we're always hearing about space junk around the Earth. Is there an issue with all these dead satellites at L2 as they run out of?
No, the satellites are so small and the orbits are so large. The volume of space there is much, much larger than the volume of space we have around the Earth itself. Because we're talking about, we're going 1 million kilometers from the Earth, and things in orbit around the Earth itself are at sort of 40,000 kilometers at most. So this is 1 million kilometers away, and we've got this huge volume there, and so there isn't really a huge problem. Yes?
For reference, how far away is Mars?
Oh, much, much further. Let's see if I can must be 2.5 astronomical units. So 1 astronomical unit is 93 million miles. So yeah.
Oh, wow.
Yes.
Those the telescopes are launching. I just like the one with that folds out. That looked kind of flimsy to me. How much of a problem is it? Like anything breaking just from the stress of launch, or like when you say within 4 microns, you could easily bend something. I would think.
Oh yeah. So this is launch shock is an enormous problem for Odin. You're always worried you have to do this G test. So lots and lots of vibration tests for Odin. One of the vibration tests was they had this very carefully calibrated giant sledgehammer that came swinging down and hit the side of it. It survived. So you do a lot of this kind of testing. That's one of the reasons why the satellites are so expensive, is that everything has to be able to sustain all kinds of different vibration modes. In fact, we delayed launching Herschel by a month because ESA suddenly discovered, as it was already being shipped to the launch pad, that somebody hadn't checked off the boxes on some of the vibration tests, and went through the whole thing and confirmed that in fact this had never been tested for this particular, 40 hertz signals horizontal or something like that, had never been tested for the mirror structure. The structure holding the mirror to the main part of the satellite. The final welding of that hadn't actually been tested at this particular frequency, at this particular direction. And so there was a whole month of extra ground tests, of, not of the satellite itself, but of sort of mock-ups quickly done to see if how stable it was. And so it's just you test. One other thing, there's 2 lessons I learned from doing this, and these probably apply to building your own stuff. One is that you never have enough testing. It doesn't matter how much you test it, you always want to test it more. And the other thing that you learn is that even though you know you can do something, that doesn't mean that when you do it, it'll actually work, because quality control is a huge, huge issue. You can know exactly all the steps of building this, whatever the box is, everything that goes into it. But if you're not really careful when you build it, you might actually not build it right so it works. And I've had this happen on about 4 different projects now where somebody slipped up. Sometimes, the last time we had Raytheon in Los Angeles, on the line where they make the infrared sensors for guided missiles. They took a couple of our wafers for one of our detectors. They had to bump on them together with the same technique that they're using. They're the only place that really can do it. They skipped a cleaning step. We had to throw away $200,000 worth of parts because they skipped the cleaning step. Who else should be doing? They should be like doing the ultimate, quality control people. They do this over and over. It's all they do in that place. Is this, and they do it for the military. We don't know how many. We don't know what they're doing. They just tell us occasionally that our project is delayed for what's the phrase they use? Secret reasons. They can't tell us why we were being delayed for several months because they got a big order for some more guided missile components. But even they will skip quality control steps. We had building our detectors at one point. I remember we had people at NIST. This is a place in the U.S. that has, they got a whole bunch of Nobel Prize winners working there. They keep winning. Every couple of years, somebody in the place wins another Nobel Prize. They're the ultimate geniuses at doing microelectronics and things. And we discovered that when they were depositing layers down on our wafers, they weren't doing it an integral number of turns. They'd done an extra half a turn somewhere. And that extra little tiny bit of layer difference across our chip made it worthless. But you don't discover that until 3 months later in testing, and at that point you've added enough extra manufacturing steps on that you've increased the value from the $5,000 component they sent you to a $40,000 component that you now throw away. So quality control is just, it's incredibly how important that is. I keep learning this over and over again. And you'd think if it comes over and over again, I don't have control over all the steps. I keep seeing the same thing going wrong with my colleagues in these projects. Yes?
Can you discuss a little bit more about why you need to keep things so cold?
Oh, most of these things, the detectors and things have sensitivities that go something like 1 over temperature to the 4th power, 1 over temperature to the 5th power. And so if you can make them colder, the better. Our current set of detectors they're all superconductors. So both in our heterodyne detectors, our spectrometers, and in our broadband detectors are superconductors. The Scuba 2 uses what's called a transition edge sensor, which works, it goes between a superconducting and normal, not superconducting state. Very, very sharp at a given temperature. And that temperature is somewhere around 120 milli K. And superconductors, have to be very, very cold temperatures for these devices. And so we actually control it down to about 60 milli K and then add heat to bring it up to where we have it just at the transition. In fact, the way that particular one works, these are great detectors. I'm going to go I'm more than answering your question. I'm going on the detector side. I can talk for hours about different kinds of detectors, and I shouldn't do that. Yes.
So the main reason that you're studying these wavelengths is because you want to see how galaxies are born, how planets are created.
Yeah. My main project is, I had to say, I'm doing about a dozen different projects. The one I'm most interested in, and it's the hardest one, I'm not sure that any of the instruments we're working on right now, ever built right now, can do it, is I'm trying to understand how water got onto terrestrial planets like the Earth. We think that all the water on the Earth came after the Earth was formed, that there was water in the disk left over as comets, and those comets rained down on the Earth. And there's a bunch of problems with that model, but it's the only model we've got. The water was certainly not from within the Earth. And so I'm trying to study other places where planets are forming to see where the water is in the pre-planetary disk. And it's a very tough problem because it's a very small size, so you need very high resolution. You need an interferometer. We don't have it in space yet.
So eventually you may be able to predict what planets.
Yeah, I'd like to be able to say, is it common to find water on terrestrial planets? Or is the Earth really uncommon? By the way, there is a lecture in, I guess, 2 weeks. 2 weeks? That you might want to know about. It's actually in one of the colleges, so it's Pascal lectures, which is religion and science, but the speaker is Jennifer Wiseman from NASA Goddard, and her talk is on extrasolar planets. And I'm sure there'll be a mixture of religion stuff in here because that's what the sponsorship of this is about. But she is one of the great world experts on looking at extrasolar planets and a very well-known scientist in planet formation, and probably well worth going to. And I'm actually in MC for the event, so I just got asked today. I think it's like February the 7th or February the 9th. There'll be notices around campus for the Pascal lectures. There's actually, I think there's a student version, which is the one that I'm emceeing. I think there's an evening one for tickets holders only. But it's one of these, prestigious lectureships on campus. Yes?
How heavy was Odin, and how much did the Russians charge you to watch it?
How heavy was it?